What if I told you there's a way to squeeze something and make part of it get bigger? I know, that sounds like something straight out of a magic show, right? Something that just completely defies the laws of physics. But this isn't a trick. It's a truly bizarre and fascinating area of materials science that is changing what we thought was possible. We all have this built-in intuition about how the world works. You squeeze a tennis ball, it gets smaller. You dive deep into the ocean, the pressure compresses you from all sides. That's just how it goes. But what if it didn't have to? What if for some very, very special materials, that same uniform pressure did something completely unexpected? Something totally backward. Okay, so on the left, you see exactly what you'd expect. You squeeze it, it shrinks. Simple. But now look at the image on the right. This is where the paradox comes to life. Under the exact same uniform pressure, the object gets squished horizontally, sure, but it actually expands vertically. It gets longer in one direction, even as it's being compressed overall. Wild, right? This very strange property has a pretty cool name, negative linear compressibility, or NLC for short. And honestly, it's one of the most counterintuitive things you'll find in the physical world. And just to be clear, this isn't some theoretical what if. It's a real, measurable property. For a long, long time, scientists only knew of a handful of materials that could pull this off, and the effect was tiny, almost unnoticeable. But recent discoveries have found materials with massive NLC effects, and that has blown the doors wide open for new possibilities. Now, I know what you're probably thinking. Hold on. This has to violate some fundamental law of physics, doesn't it? I mean, how can something get bigger when you're literally pushing on it from all sides? Well, it turns out there's one crucial rule that makes this whole thing possible. And here it is. This is the key to the whole puzzle. The total volume of the material must still decrease. That is the non-negotiable law of thermodynamics. There's no getting around it. The trick, the absolute genius of these materials, is that they found incredibly clever ways to shrink in 2 dimensions so much that it gives them room to expand in the third, while the whole thing still gets smaller overall. And just so we're all on the same page, we're talking about a very specific kind of pressure here. It's called hydrostatic compression. The best way to think about it is imagining an object deep, deep underwater. The pressure is pushing on it equally from every single direction at once. That's the special condition that makes this bizarre expansion happen. So, at the end of the day, this isn't magic, it's just mechanics. Really, really clever mechanics. The materials that show NLC aren't breaking the rules, they are exploiting them with some incredible internal structures. So let's dive in and look at the 3 main ways they pull off this geometric sleight of hand. Okay, this first mechanism is all about sudden, dramatic change. Some materials, when you squeeze them hard enough, basically decide they've had enough of their current arrangement, and they abruptly switch their entire internal atomic structure. A fantastic example is a material called paratellurite. So at normal pressure, its atoms are arranged in this nice, stable, rutile structure you see on the left. But as you start to crank up the pressure, its internal columns of atoms start to rotate and tilt until, bam, it just snaps into a totally new, more compact arrangement, the CSCl2 type structure on the right. And this graph, this is the proof. As you increase the pressure up to about 0.9 gigapascals, all the dimensions shrink, just like you'd expect. But look at what happens right at that transition point. See that blue line? It represents one of the dimensions. It suddenly changes course and starts to get longer, even as the pressure keeps going up. That's NLC in action, born from a structural switch. Okay, so that first one was a sudden switch. This next mechanism is a bit more elegant. It isn't a snap change, but a continuous mechanical motion that's built right into the material's atomic structure, like a whole bunch of microscopic hinges. Think about a wine rack, or maybe one of those scissor lifts. If you push down on the top, what happens? Of course, it flattens out, but it is forced to expand sideways. It has no other choice. Well, some materials are built with that exact same geometric principle, just at the atomic level. And this is a brilliant illustration of that concept in a real material. This is a compound called BiB06. When you apply that uniform pressure, these groups of boron and oxygen atoms act just like little hinges. As they tilt and rotate to handle the pressure, they force the entire structure to expand along one specific direction, just like that wine rack. It's pure mechanics. The third mechanism is, well, it's maybe the most elegant of all, because it's a design that nature itself uses all the time. It's based on one of the most fundamental shapes in the entire universe, the helix, or, the spring.
Yeah, in fact, this is the same idea that allows some worms and squids to move around. They actually use helical arrays of tendons that get shorter when they're filled with fluid, an effect that's directly related to NLC. And it turns out some elements are built pretty much the same way.
So get this. This is the atomic structure of the element tellurium. It's not just a random jumble of atoms at all. It's an ordered array of tiny, perfect helices, all packed together in a bundle. Each one of those chains of atoms is basically a microscopic spring. So what happens when you put this under pressure? Two things happen at the same time. First, the helices get pushed closer together, which causes the material to shrink side to side. But at the same exact time, the pressure makes each individual helix uncoil just a tiny bit. And just like untwisting a spring, that uncoiling motion makes it longer. That's negative linear compressibility along the length of the springs. So these three incredible mechanisms, the sudden switch, the geometric hinge, and the uncoiling spring, they're so much more than just a scientific curiosity. Understanding them gives us a blueprint, a kind of design manual, to build new materials that can do things we really once thought were just impossible. And this brings us to the really exciting part. What can we actually do with this? I mean, imagine artificial muscles that contract powerfully just with fluid pressure, no electricity needed. Or think about hypersensitive pressure sensors that amplify a signal by physically expanding in a measurable way. We could build precision actuators for tiny machines, or even shock absorbers that respond to an impact in a totally new and useful way. The ability to make something grow by squeezing it really pushes the boundaries of material science. It transforms what was once a physical paradox into a real engineering tool. And it leaves us with this huge, fascinating question. If we can now design materials that defy our everyday intuition, what other impossible things are just waiting out there for us to build?